imagine taking an application that cost millions of dollars to compile, a system built by absorbing basically an entire internet's worth of data. And then you just decide you're going to rip it open and overwrite its foundational source code right on your local machine.
It sounds kind of reckless when you put it like that.
Right. But that is effectively what you're doing when you embark on full fine-tuning of a large language model. Welcome to the deep dive. For all the software engineers out there who are, currently burning the midnight oil, navigating the absolute wild west of AI development, tonight we are looking at the ultimate heavy-duty upgrade.
Yeah, we are talking about taking an off-the-shelf, pre-trained AI and literally updating every single parameter inside of it.
Exactly. And we're going to unpack the actual mechanics of what it takes to pull this off.
Yeah.
Because reaching for that maximum adaptation power,
Yeah.
the ability to make an enterprise-grade model entirely your own, it demands a massive toll.
It's the absolute maximum power move in machine learning. I mean, you are no longer just asking the model to learn a few new tricks via a text prompt. You are fundamentally altering its brain structure.
Yeah, and we'll look at the hardware tax at doing that, the terrifying hidden danger of accidentally lobotomizing your AI.
Right.
And when a development team should actually pull the trigger on this versus using much cheaper alternatives.
Because the allure of full fine-tuning is incredibly strong. Developers see an open source model and immediately think, oh, I need to rewrite the whole thing to fit my specific use case.
Right, I need to make it mine.
Exactly. But doing so requires a really deep understanding of what you are actually demanding of the hardware. The physics of the process are entirely different from just chatting with an AI.
So let's talk about that physical toll first, because you can't just run this process on a standard laptop or, even a typical high-end gaming rig, can you?
No, absolutely not.
When we move from just running a model, what we call inference, to full fine-tuning, the memory requirements just completely explode. The baseline rule is that full fine-tuning requires roughly 7 times greater memory than inference.
Yeah, and that 7 times multiplier is the number that usually makes engineers sit back in their chairs and reconsider their weekend projects.
Oh, for sure.
Let's look at inference first, just as a baseline. When you are just generating text, you are simply loading the model's weights into your GPU memory. So if you have a 7 billion parameter model and you load it in 16-bit precision.
And just to clarify, for the traditional software engineers making the jump to AI, 16-bit precision simply refers to how many decimal places the computer uses to store each of those 7 billion numbers, correct?
That's a great way to put it, yeah.
So heavier precision equals a physically heavier model in memory.
Exactly. At 16-bit precision, each parameter takes up 2 bytes. So a 7 billion parameter model is, well, a 14 gigabyte file. To run inference, you just load those 14 gigabytes into your VRAM, you pass a text prompt through those layers, and you get an output. It is a static, read-only process.
Which fits on a lot of standard high-end consumer hardware.
Right.
But switching to full fine-tuning changes the entire paradigm. So if the model itself is only 14 gigabytes, what on earth is taking up the other 80 to 100 gigabytes of memory to hit that 7 times tax? I mean, are we just saving copies of the model?
Not exactly. We are saving the specific mathematical objects required to learn. The transition from reading to writing is incredibly heavy. So first, we have to store the gradients.
Okay, gradients. I always hear gradients described as like the slope of the error. Is it basically the mathematical direction telling the model which way to adjust its weights to get a better answer?
Yes, exactly that. For every single parameter in the model, the training process calculates a corresponding gradient. So if you have 7 billion parameters, you now need to store 7 billion gradients in memory.
Wow. So you've just doubled your footprint right there.
Right. But you don't apply those gradients directly to the weights. You feed them into an optimizer. And in modern machine learning, that is almost always the Adam optimizer.
Okay, but what makes Adam so memory intensive?
Well, Adam doesn't just look at the current error. It looks at the history of the errors. It keeps a running average of the gradients and a running average of the squared gradients for every single parameter.
Wait, why does it need a running average? Why not just fix the immediate error and move on?
Because if you just react to the immediate error, the model's learning path gets incredibly jittery.
Oh, I see.
Yeah, it would overcorrect constantly, kind of like a driver jerking the steering wheel back and forth on the highway. The running averages act like shock absorbers. They smooth out the learning trajectory so the model converges reliably.
But the cost of those shock absorbers is steep, I'm guessing.
Very steep. For every single parameter, Adam is holding on to 2 additional variables in memory.
Okay, let's do the math on that. For a 7 billion parameter model, we have 7 billion original weights, then 7 billion gradients. then 14 billion optimizer states for Atom. We are already at 4 times the memory.
Yep. And we haven't even talked about the activations yet.
Oh, man.
And activations are the final massive chunk of the memory tax.
What are we actually storing there?
Think of a neural network as an assembly line with dozens of stations or layers. When you pass a batch of training data through the network, which is the forward pass, you have to save the intermediate mathematical outputs of every single layer along the way.
Because you need them for the back propagation later, like
Yeah.
to figure out what went wrong.
Exactly. When the model reaches the end of the assembly line, it calculates how wrong its answer was. Then it sends that error signal backward through the network to update the weights. You literally cannot calculate how to fix the error at layer 2 unless you remember the exact mathematical state layer 2 was in during the forward pass.
Man, so it's kind of like running a massive software application locally in your IDE.
How do you mean?
Well, running inference is like shipping the compiled app to the user. It's lightweight, the code is static, it just takes an input and gives an output. But full fine-tuning is like running that app with the debugger attached, right? With a heavy memory profiler running in the background, keeping every single source file open and tracking every single variable state change in real time so you can step backward through the code if something breaks.
That is a brilliant analogy. Yeah. The debugger, the profiler, the state, tracking those are your gradients, your optimizer states, and your activations.
Wow.
And in a deep network with dozens of layers and thousands of tokens in a batch, storing all those intermediate states takes up a breathtaking amount of VRAM.
I mean, there is nothing more universally soul-crushing for a machine learning engineer than hitting run, waiting 10 minutes, and getting slapped with a CD out-of-memory error in PyTorch.
The dreaded And that happens so often because people severely underestimate this transition. When you add it all up, that baseline 14 gigabyte model suddenly requires nearly 100 gigabytes of memory to full fine-tune. You cannot even fit it on a single, top-of-the-line, 80 gigabyte A100 GPU without deploying specialized memory-saving tricks.
Okay, so let's say you've paid the toll. You've provisioned the massive GPU cluster, you're paying the hourly cloud costs, and you have this heavy machinery ready to go.
Yeah.
Now you actually have to steer the ship. And driving this machinery is incredibly delicate, isn't it?
It really is, and it is entirely about the learning rate. In the context of full fine-tuning, the learning rate is the single most critical hyperparameter you will configure.
Right, and the consensus seems to be that your fine-tuning learning rate must be, 10 to 100 times smaller than the rate used during the model's initial pre-training from scratch. We're talking about dropping down to microscopic numbers like 1E5 or 5E5.
It absolutely has to be microscopic. Consider what a pre-trained model actually is. It has already consumed a massive fraction of human knowledge. It has mapped the structure of language, logic, reasoning, facts, syntax. It's a highly tuned, deeply entangled system of weights, carefully balanced to produce coherent thought.
Right.
So when you engage full fine-tuning, you are suddenly turning all 7 billion dials at the exact same time.
What happens if a developer just, ignores that and sets a standard learning rate like 1E3?
You watch your training logs, and suddenly your loss function just outputs NAM.
Not a number.
Not a number. The math has literally exploded. You've introduced such a violent shock to the system that the weight updates spiral to infinity.
Oh, wow.
And even if it doesn't hit NAN, a high learning rate causes weight updates that are too large, which completely shatters the foundational representations the model learned during pre-training. You take a sledgehammer to a Swiss watch.
Which leads to the central, probably most terrifying risk of full fine-tuning.
Yeah.
Catastrophic forgetting. The phenomenon where teaching a model a new task completely overwrites its general knowledge.
It is the nightmare scenario for any AI deployment. The model learns your new data set, sure, but suddenly forgets how to string a coherent English sentence together.
Okay, let me play devil's advocate here on behalf of a developer listening right now.
Sure, go for it.
Let's say I am an engineer at a fintech startup. I am full fine-tuning an AI specifically to write complex SQL queries for my company's highly proprietary database schema. If it learns to write perfect SQL for my backend, why do I care if it suffers catastrophic forgetting and loses its general knowledge of, say, 18th century French poetry? I don't want it writing poems. I want it writing database queries.
That is the most common pushback we see from engineering teams. The assumption is that an AI's brain operates like a filing cabinet, right? Poetry goes in one drawer, Python code in another, SQL in a third.
Right, so if we burn the poetry drawer to make more room for SQL, who cares?
Exactly. But neural networks do not store information in isolated drawers. Knowledge relies on distributed representations.
Meaning, what, the same neurons that fire for analyzing a poem might be heavily involved in structuring code.
Exactly that. The foundational capabilities that allow a model to write SQL understanding logical flow, tracking variable dependencies, recognizing hierarchical structures, grasping the nuances of complex instructions, those core reasoning capabilities were built by reading everything.
Oh, interesting.
Yeah, the linguistic reasoning that lets a model parse a complex, winding sentence in a history book is the exact same underlying logic engine it uses to parse a multi-join query requirement.
Oh, wow. So if I aggressively overwrite the poetry weights to force-feed it my specific SQL syntax, I might accidentally be lobotomizing its underlying logical reasoning skills entirely.
You will end up with a model that memorizes your specific database column names perfectly, but completely fails to understand the logic of the prompt you actually give it.
It just breaks.
Right. It loses the ability to reason about the code it is generating. That is why that tiny 1E5 learning rate is non-negotiable. You have to delicately fold your new SQL knowledge into the existing neural pathways without disrupting the foundational logic architecture.
Okay, so how do we actively prevent that lobotomization then? Beyond just setting a tiny learning rate, how do we salvage the brain while still pushing the model to adapt to our custom data?
There are two primary structural mitigations developers use: data mixing and gradual unfreezing.
Okay.
Let's look at data mixing first because it directly combats the catastrophic forgetting problem during the training loop itself.
So essentially, are we like sneaking vegetables into their food? Like if the model only wants to eat your custom SQL data macaroni and cheese, you have to blend in the general knowledge vegetables so it doesn't get intellectually sick.
That is a surprisingly perfect way to frame it.
Next.
If you only feed it macaroni and cheese, it loses its foundational health. In practice, developers create what is called a replay buffer. Let's say your fine-tuning dataset has 10,000 examples of your custom SQL. You do not just train on that. You mix in, say, 1,000 or 2,000 examples of high-quality, general instruction-following data.
Stuff like standard conversational prompts, math word problems, general coding tasks.
Precisely. As the optimizer calculates the gradients and updates the weights, it is constantly balancing the updates between learning your specific database and maintaining its general intelligence. The general data acts as an anchor.
Ah, constantly reminding the model of its foundational reasoning skills so the SQL data doesn't just pave over them.
Yes.
What about gradual unfreezing? How does changing the sequence of training help protect the model?
So gradual unfreezing leverages the physical architecture of the model. A language model is composed of many transformer layers stacked on top of each other, maybe 32 or 40 layers deep. The lower layers, the ones closest to the initial text input, they tend to capture very basic fundamental features of language: grammar, syntax, fundamental word relationships.
And the higher layers, the ones closer to the final output, handle the more complex, abstract, task-specific logic.
Yes. So if you hit all 40 layers at once with your new, highly specific SQL task, you risk sending shockwaves all the way down and destroying those foundational grammar layers. With gradual unfreezing, you don't update everything on the very first pass through your data set, what we call Epoch 1. You actually freeze the bottom layers entirely.
Like you tell the PyTorch optimizer, do not calculate gradients or change weights for layers 1 through 20.
Exactly. You only let the top few layers adapt to the new task initially.
So,
Then, slowly, over the course of subsequent epochs, you gradually unfreeze the lower layers, letting them make very tiny, stabilized adjustments. It prevents massive, sudden shocks to the model's core linguistic engine.
man, considering the sheer headache of all this, managing a 7x memory explosion, dialing in microscopic learning rates to prevent NaN errors, sneaking data vegetables into the mix, freezing and unfreezing specific transformer layers, when is it actually worth an engineering team's time to do a full fine-tune?
It is a phenomenal question because full fine-tuning is widely overused by beginners. It really makes sense only when three specific conditions are met in an enterprise environment. First, you need a large, highly unique data set. We are talking tens or hundreds of thousands of high-quality examples representing a domain the base model has never encountered before.
Okay, large, unique data set. Second condition.
Maximum performance must be absolutely critical to the business model. And third, you must have the serious compute infrastructure and budget ready to handle that memory tag.
Meaning, if someone is thrown together a weekend sprint to make a customer service chatbot for a small e-commerce site, and they only have like 500 examples of past chat logs, full fine-tuning is the wrong tool.
It is considered total overkill. If you only have 500 examples, full fine-tuning a 7 billion parameter model will almost certainly lead to immediate overfitting.
Hmm?
The model will just memorize your 500 examples, lose its ability to generalize, and break. Full fine-tuning is an enterprise-grade deployment tool designed for massive domain adaptation.
Right. Let's talk about the final bill then, the actual compute costs. Because accessibility in AI is changing rapidly, but the hardware demands scale brutally. For a 7 to 8 billion parameter model, which is the sweet spot for a lot of local open source development, right now, doing a full fine-tuning run takes roughly 4 to 8 hours on a single A100 GPU.
And realistically, a developer can rent a single 80 gigabyte A100 on a cloud provider for maybe $2 to $4 an hour. So you are looking at $15 to $30 for a full fine-tuning run. At that scale, it is incredibly accessible.
But stepping up to frontier-class open models changes the math entirely, doesn't it? If a company wants to full fine-tune a massive 70 billion parameter model, the costs do not just scale linearly.
No, because of that 7x memory tax, a 70 billion parameter model needs hundreds of gigabytes of memory just to exist in a training state. You are no longer renting one A100 for an afternoon. You are provisioning a massive multi-node cluster of GPUs connected by ultra-fast networking, and you are running them for days or weeks.
Wow.
Suddenly, that pushes the compute costs into the tens of thousands of dollars per run.
Which is a terrifying budget to ask for if you aren't absolutely certain your learning rate is perfectly dialed in. You could burn $30,000 of compute budget only to realize you induced catastrophic forgetting on Tuesday.
The financial risk of experimentation at that scale was becoming a massive bottleneck for the industry. Developers needed a clever alternative. They needed a shortcut. And that shortcut is LLM.
Low-rank adaptation. This technique genuinely democratized fine-tuning over the last few years. Because instead of updating all 70 billion parameters and paying that crushing 7x memory tax on every single one of them, LoRa updates only millions of carefully chosen parameters.
The math behind LoRa is a brilliant piece of engineering. It operates on the assumption that while a neural network is incredibly massive, the actual changes you need to make to adapt it to a new task do not require moving all 70 billion dials independently.
How does it actually achieve that memory savings mechanically, though? I hear the term low-rank matrices thrown around all the time, but how does that compress the workload?
Let's visualize a layer in the neural network as a massive grid of numbers. Say a grid of 10,000 weights a 100 by 100 matrix. Updating that layer normally means the optimizer has to calculate 10,000 new numbers.
Right, paying the memory tax on all 10,000.
Yes. But LoRa uses a mathematical trick called matrix decomposition. It freezes that original 100 by 100 grid completely. No gradients, no optimizer states. Then it creates two tiny new grids that sit right next to it, say a 100 by 2 matrix and a 2 by 100 matrix.
Oh, and if you multiply a 100 by 2 and a 2 by 100 matrix together, the resulting shape is still a 100 by 200 grid.
You've got it. It produces the exact same shape needed to interact with the network, but you only had to train 400 parameters to get there. 200 in the first grid, 200 in the second.
That's incredible.
Yeah, you effectively bypass training 10,000 parameters and instead only train 400. It is pure mathematical compression.
It is wild. So you inject these tiny sidecar matrices into the layers. You were training maybe 10 million parameters total instead of 70 billion. The memory requirements drop through the floor, the cloud costs drop to a fraction, and the risk of catastrophic forgetting is heavily mitigated because the original 70 billion parameter brain is completely frozen and untouched.
Exactly. The general knowledge is safely locked away, while the tiny LoRa matrices handle the specific adaptations.
Okay, I have to challenge the enterprise use case here, though. If LoRa achieves performance that is surprisingly close to full fine-tuning, and it does it by only updating a few million parameters for like $20, why on earth would any engineering team ever spend tens of thousands of dollars and risk catastrophic forgetting to update all 70 billion parameters? It seems like an unjustifiable risk.
It sounds totally unjustifiable until you look closely at what surprisingly close actually means in high-stakes environments. Let's return to the 3 criteria for full fine-tuning. The second requirement was maximum performance is critical. In many standard domains, the performance gap between LoRa and full fine-tuning might only be 1 or 2% on a final accuracy benchmark.
Right, and for a standard customer service chatbot, no one cares about a 2% difference. You use LoRa every time.
But what if you are a massive quantitative hedge fund training a 70 billion parameter model to parse real-time global financial news and generate high-frequency trading signals? Or, say, a biotech firm fine-tuning a model on millions of proprietary protein sequences to discover new pharmaceutical drugs?
Okay. In those environments, a 1 or 2% increase in accuracy isn't a minor optimization. It's hundreds of millions of dollars or a life-saving medical breakthrough.
Precisely. When the stakes are that monumental, a $30,000 compute bill is just a rounding error compared to the upside of absolute maximum adaptation. When you are operating at the bleeding edge of a highly specialized, bizarre domain like complex mathematics or protein folding, you want the model's entire linguistic and logical foundation to perfectly align with the physics of your unique dataset. LoRa cannot always bend the underlying foundation far enough to get you that final 1%. Full fine-tuning can.
That makes total sense. Well, let's summarize the journey we've taken in this late-night session. We started with the sheer, raw power of full fine-tuning, the audacious ability to rebuild an off-the-shelf model into a custom engine. But we uncovered the massive physical toll, the 7x memory tax required just to load the gradients, the moving averages of the atom optimizer, and the forward pass activations.
We navigated the incredibly delicate steering required to prevent the math from exploding into nans, dropping the learning rate down to microscopic levels to avoid shattering the pre-trained weights.
We looked at the nightmare of catastrophic forgetting, realizing that poetry and SQL actually share the same logical pathways, and how to mitigate that risk by sneaking general knowledge vegetables into the training diet and gradually unfreezing the structural layers. And finally, we weighed the brutal realities of scaling costs against the brilliant mathematical compression of LoRa matrices.
It really forces developers to deeply understand the physical and mathematical constraints of the medium they are building in. You aren't just writing code anymore, you are shaping a neural architecture.
Absolutely. Before you get back to your terminal, I want to leave you with one final thought to mull over while you are staring at your code. We talked about how the matrix decomposition of LoRa can achieve nearly the exact same performance by only tweaking a few million carefully chosen parameters instead of all billions of them. If that mathematical compression works so incredibly well, what does that tell us about the foundational models themselves?
That's a great question.
Right. How much wasted space or hidden redundancy actually exists inside these massive 70 billion parameter monoliths to begin with? If we only need to move a fraction of a percent of the weights to change its behavior entirely, maybe the giant AI brains we are building are far more hollow than we thought.
That points to a fascinating ongoing debate in the field right now about the true intrinsic dimension of these models.
Something to keep you awake for the rest of the night. Keep building, keep questioning the underlying mechanics of the tools you're using, and we will catch you on the next deep dive.